over 5 before, that's why. But anyway, it doesn't change the fact that we have the exact same system here of the helicopter. We have the systems and the bases and everything is the same. It's just so we got that point, and maybe this now looks a little bit different. We had 98% before, which was a lot, but it didn't really make sense also with the simulation there. That's why I reacted. But this looks more in line with that, and this is what we want to improve, and that's the task we have at hand. And I have to really sit tight to this microphone for it to work. But anyway, we had 3 suggestions on how we could improve this solution. Either we could buy more spares, we could replenish. That means buying more spares and trying to move up here in this diagram to get higher availability. We can also try with a different storage strategy, that we can try to store items at all stations. And the third option was to shorten the transportation times, and in that way try to improve the solution. But first of all, we start with this replenishment, buying more spares. So what I'll do is to go back to the input, and I know that even though I didn't understand all of it, I know that Yang told you about it, but in the control parameters table, we did the analysis, but now we want to do the replenishment instead. So buying more spares from a given set of items. When I work with the OPUS Suite and the files, when I change something, I always change the name. I save the file with a new name, so I get 2 files. And so by doing this, if I do this file and I go save as, this is just as with Excel or Word or anything. You see here that I have this analysis case that we're just looking at, but now I want to do, rather than analysis, I want to do replenish. So I call it REPL. So now if you see here in the file explorer, I have 3 files, right? So I simply copied the one that I had, but I just saved it with another name. So now the benefit with this is that I have 2 files so far with the exact same information, but I can adjust the information I want to in one of them, and then I can simply compare them in the result window. So we are in this replenishment file. I actually did change to replenishment here, the problem type. But I need to do one more thing, and I need to move the stock allocation from being an allocation to being something that exists. So I copy here, and I'm going to insert a table called stock exists instead. So, and I just paste the data here. So the item identifiers at the central station, because that's the only station where we can allow spares, and 3 of each, as you remember. So that's really all I need to do here, and I can run this file like this, pressing the calculate button. It asks if I want to save it. Yes, I want to save it, and that went so fast so you didn't even see that we performed the calculation. But what happened here is that you see on the right, you see the cases that I have open in this result diagram. I have the original one, the one that was called helicopter basic analysis, and then I have helicopter basic replenishment. So if I click this one, you see it will select, it was just 1 point. It was this 76.7%. And if I click the other one, you see it will be on top of it. Well, if I go to the first point on this curve, so it starts from the very same solution, 3 of each. But then it starts to add more. I can zoom in this graph. It makes it a little bit easier to follow. So just click and drag. I can zoom in the graph. So I come a bit closer in. Now I can move along the curve here, going up. You see, buying some more spares will increase the availability to 77.7% instead. Then I can continue moving upwards on the curve, and you see how the availability increases. But also, of course, the x-axis, because this means that we buy additional stock. And of course, we can compare. So let's say we want to reach 90% availability. This point is the first one above this 90% criteria. If I move to the up here, I showed you before, the result table view. And I look at the item results instead. And I'm just going to select the stock size parameter, showing the number in stock. So, okay, and then we're only interested in the central station here. So on the left, we have our 8 items. Here we have the central station, and you see the original analysis case is 3 of each. And here on the right, we see the suggestion from the optimization on how we should increase our stock solution in order to get an availability of 90%. There are some functions here. We can, for example, anchor up here and show a delta. We can see, okay, wrong one. So sorting this data here, we see that, okay, it's a compressor blade. I should go from 3 to 5, meaning I should buy 2 additional ones. For the turbine module, also 3 to 5, 2 additional ones, and so on. So this is another way of representing this increased investment in spare parts. And again, going back to this, to the graph view here, we see that we could actually, that we improve this with from the original 76% to the 90%, and we can, if I do a point diff here, we can see that the total diff in life support cost here is 7,660. So not that many percentage in increased costs, but considerable increased availability. So that's one way of doing it. But let's say that we should try something else. We wanted to try the local storage, because if we're looking at the graph on the top here, you remember that the color here on the stations represent some different characteristics of the stations. And the ones at the bottom here, the operational bases, they cannot hold any stock. So it means that we have all stock up here. So maybe it's better to store stuff down here instead. And we can try that. To see if it gets better. We continue from the replenishment case where we add more spares because that was interesting. So again, I do the same thing. I do file, I do save as, and I create another file that we not only call replenishment, we also call it local store. That's a good name. So, okay, so that's the local store case, and this is a property of the station. So in the organization category, go to the station table. Here you see the type of those stations. So it's really simple. I just remove this operation type here, delete. You saw now they all got the default value of a depot, and they also turned green here. This means that we are now allowed to add stock at those stations as well. Let's do that. Run again. We can run the scenario and calculate. And we see, I zoom in the graph and a little bit, come closer. We see that in the beginning, it's not a big difference, probably because we are adding spares to the central storage. But then you see how those blue points, which represent the one with the local store, actually gets higher availability for the same investment. And that's because we start adding stuff at the local stores as well. So why is that better? Well, it's because if we can have spare parts closer to the systems, the waiting time will be shorter. So the time that the systems are still or not in operation will be shorter, so the availability will be better. So that's why it's zoom out a little bit here just to show if you want to go for zoom up here instead a little bit. So this means that we actually can reach, in the end, you see that we can reach availabilities that are above 99% up here when we have the local storage, because we simply can have spares closer to the systems. In the other case, this curve is flattened out around 98%, because here we can only store stuff at the central station. But what's interesting here also is to compare. So let's say we have a 98, first point above 98%, this one, then first point above 98% is this one. And then we do that, comparing those 2 points. You see you get a black line between the points, so we can get the difference between them. So same availability, 98%, but we can get those 98% with, if we allow storage at the local stores, then we see that the cost here is 17.8 thousand. So now it's a small case, but what we can tell from this is that it could be worth investing some money in allowing spares at the operational basis as well, because it will increase the availability. And here also is an indication of how much we can spend in such an investment, because we are saving money on the spare parts. So again, it's this trade-off between the cost and the effectiveness that we reach out of it. So I think that's really this kind of analysis is really what RAMC analysis and cost optimization is about, to understand what the impacts are of different decisions and to evaluate them. Okay, we had one third alternative actually, and it was to, if you remember, it was to shorten the transportation times. Okay, so let's do that. We can start again from that replenishment case with only to make it, to compare how effective it was. So I start from this. I open this replenishment case, and then I again use this file save as. And we call it replacement short transport. Right, and what we're going to do here is to shorten the transportation times for between the central and the bases. This property is part of the station structure table, right? If you recall, we gave really long times here to the mother station, so long transportation times there. So in the Excel file, we had some suggestions on so here it says, so okay, maybe we can decrease to 48 and 100 hours instead. You can set, of course, any value here, but let's use that. So sort of half of that long transportation time. And then you think, how much does this affect the total availability and cost? Well, we run it. So we use that calculate button here and run that scenario. Now I used the local store anyway, but it doesn't really matter. Now I continued from this situation where we were allowed to have storage at the bases. Anyway, I have too many files open at the same time. So what I did was that you see here on the left, I was a little bit quick starting to adding the values here in the table, but I was in the wrong file. So you see here is the replenishment local store case, but I actually created one that was called short transport down here. So I have to be aware here when I have many files open at the same time, so I'm working in the right one. So there we go to the station structure there instead. And I said 48 and 100. So half the transportation time. This is the scenario where we have no spares at the bases, right? So that's it, run the calculation, and let's see what that gives us. What happens now is that, zoom a little bit here, you see now this is the purple curve here, so those points. You see that for what happened now was that we sort of jumped up from the original solution or the original situation, and we got higher availability with no additional cost. And that's because we simply shortened the transportation times, right? But we didn't add any costs. So then we just improved the solution. So that's why we got better availability at the same cost. But then again, if we do replenishment, you see that, okay, so we can increase availability, and then it will flatten out. And somewhere here, you see in this area where it's pretty tight between the curves, you see that they are crossing each other. And what happens here is at this point, it actually gets better to invest in the local storage rather than investing in shorter transportations. So this means that if you want to reach higher availabilities, and we want to go up towards 99% here, we need spares closer to the systems. So initially, for lower availabilities, it's a smarter choice to go for the shortened transportations. But if we want to reach the really high availabilities, we need to have local storage instead. And also you can compare, well, now I did not add any costs for the shorter transportations. Maybe it's more expensive to send stuff in the fast way. So what we can compare here, for example, if we look around 95%, we compare those 2 points. Okay, so we can, it means that we have sort of the limit of the cost, or the difference in cost is approximately 2,600 in this case. So that's how much it possibly could be worth investing in this faster transportations. So always remember to relate the improvements to potential costs and so on. So what is this investment worth, and so forth. Okay. Right. Okay, so that's how we can improve the model, some different ways of improving this current situation that we are in. We're going to move on and look at some just have to make sure where I am. Okay, save that part. Anyway, so here's a few words on how the optimization works. I think it's kind of interesting. I hope you do too. Tired of this microphone that I have to hold close to my mouth all the time. Anyway, so this is what it looks like. We have our model here, an example again. So, and as we said, if we start, when we run like an initial calculation, we start with zero stock. It means zero costs, no investment costs here. But probably we will still have some kind of availability because the items will get repaired eventually. So we will end up with some availability above zero. And then, as we start to invest in spares, we go. So maybe the first stop. What's happening? Oh. I'm not friendly with this animation. That's clear. Anyway, so forget it. Whatever. The point is that what OPUS 10 does is when we move up on the curve from one point to the next, I use manual instead of animation. So down here we had no stock at all. And then OPUS, what we're doing is we look at what options do we have in investment of spare parts. Well, we can invest one of the yellow one, or one of the red one, or one of the blue ones. And OPUS sees here, okay, what happens with the curve? If I buy a blue one, I might end up here. If I buy a yellow one here, or a red one up here. And then what we're doing is to select the one that gives us the steepest increasement in availability for the invested cost. And that's something that's called marginal allocation. So we are being smart when we select how to invest in spare parts. And then we start from there. We go on from that point where we bought one of the red ones. And then again, what can we buy? Either a yellow one, another red one, or a blue one. And we look at the curve, which one gives the best improvement in availability according to the additional cost. And that's really how it works. It continues up until we have created the entire curve. And now I give a very simple example. And of course, I mean, if we have a real-world system with hundreds of items, and we have a real-world support organization with 10 or 20 or 30 different sites and stores, etc., that becomes a really complicated task to do by hand or in an Excel sheet or something like that. So that's why we need a software like OPUS. I'm just saying that there are no secrets in the mathematics. Those are well-known algorithms that are used, but with the smartness of OPUS, we can handle really large solutions and cases as well. And also there are no limitations, of course, in the number of echelons, as it's called, or levels, both in the support organization and in the breakdown of the structure of the systems. And what you can say here is that the curve can be this different angle, or the steepness of the curve will change. So typically how a curve like this looks is that for the first points, the early points on the curve, the cost per increase in performance is often quite low. It means that the curve is pretty steep. So we can, by small additions in cost, we get a lot of availability increasement. However, as we move up higher up on the curve, it will be a much higher cost for small increases in performance. That's kind of natural. To try to push it a little bit more will cost more and more as higher as we go. And for all setups, this curve will sort of flatten out somewhere. And this is good to know. So at some point in time, it's no idea to invest in more spares because it won't give us any more performance. That's also something good to understand when that happens. So, I mean, yeah, someone says, we need more availability. Well, buy more spares. You buy 10 more of each spare part, but it doesn't help you anything because that's not the problem. There are other reasons for this unavailability. There are some different result categories we've looked at. Talked about the system reliability, mean time between failure, mean time between maintenance, mean time to repair. There's also something called an inherent availability, which means that this is the maximum availability that we can get out of this system if there are no other delays. We can also get results around forecasting of the maintenance volumes and cost. We looked at this a little bit both in OPUS 10 and Symbox before. So we can look at the number of demands for each item and at each station. Repair volumes, how many repairs are being performed, also PM when we add that to the model. How many transports are performed, what are the maintenance costs. We can also look at consumables, which we'll get back to later on. And then we can get the optimized cost and performance. I think this is nothing that we haven't said already, but investment costs, of course, what is it, how much do we pay for each spare part? What's the performance of the systems? Stock allocation, meaning how many of each part should we store at the different locations. Same thing for resources, and then also reorder policies for spare parts. If there are, if you remember, I mentioned before that some parts might not be possible to repair, but we have to discard them and buy new ones, then we can, for those items, we can also produce reorder policies. A reorder policy means typically at what level should we perform the reorder, like if we drop to a certain level, when we should buy more, and so on. Okay, so it's important to remember that when we look at the Opus 10 results, it is a deterministic mathematical model with steady state results, which means that those are average results. This is, we are always, when we look at things, it is averages. It's not specific things happening at a certain point in time. We're always looking at average values over a longer period. That's important, and that goes for all the results when we look at this model. And also the stock sizes that are suggested, those are the nominal number of items in stock. It doesn't mean that we have that number of items in stock all the time. If Opus 10 suggests us to have 5 items in the stock, that stock size in reality will vary a lot over time. But with Opus 10, we only calculate that nominal number of items. So how many should we invest in? And then there will be, we talk about the repair loop. So items that are taken out of the system, sent for repair, they are in the repair loop. So all of that won't be in the stock, but some of them will be in repair. Yeah, and this one is, when we look at Opus 10 and the results, we are always having the system approach. The system approach means that we start from, we always take the start from the system performance and what is the characteristics of the system. So the system effectiveness is what's important. There are other approaches, more that often are used and in many applications and around the world, and we see this as sort of a competitor to what we do. And I just want to spend a few minutes on explaining why we think it's so important with this system approach rather than looking at item by item. Okay? So when people use this item by item method, they often start from the risk of shortage for an item. So what is the risk that we don't have a spare part when we need it, right? Something fails, we need a spare part. So if we take a very simple example here, we have 3 items, 1, 2, and 3. We assume that there is a mean time between failure here, and there is a turnaround time on the repair of those spare parts. Okay, and then we say that we have 10 systems here, and we are flying 500 hours per year. And with this as input, we can, with some simple mathematics, calculate the risk of shortage, depending on how many items we have in stock size. Okay, so I actually did this in Excel for preparing this presentation, and it's quite easy. So if we have, for item 1, if you have 0 items in stock, the risk of having a shortage when we need it is, of course, 100%. If there's never any item in the stock, there will always be a shortage. That's what risk of shortage is. So 100% risk of shortage if there are no one in stock. However, if I buy 1 item of this item and put it in the store, then with these characteristics and the formulas for calculating risk of shortage, it means that it's only a 15% chance that I have a shortage if I have 1 item. And then, now it's really small, but if I buy another one, I have 2 items in the stock, it's only 1% chance that it's a risk. And of course then, 3 or 4 in stock, yeah, the risk is almost done at 0. If we do the same thing for item 2, of course, 0 items in stock will give us 100% risk of shortage. And depending on the characteristic here, and if you compare especially the mean time between failures, you see that it's only 280 hours between failures for item 2, while it was 2,500 for number 1. See here the difference. Right, that means that there are much more failures for this item. So if I buy one item 2 and put in the store, I'll have a 77% risk of shortage. So much higher than item 1. And then if we continue, buy 2, the risk is 43%, 3, 18, and I need even 4 items of this one in the stock to come down to 6%. And then we can do the same thing for item 3, of course, 100% if you have risk of shortage, if there are no items, 46 if you buy 1, etc. Okay, why do I do all this? Well, as I said, in many contracts that we see between customers and operators, they say, okay, we stipulate that we should have maximum 10% risk of shortage for each item. That's kind of common. Some of you are nodding, maybe you recognize this. And okay, so if we should do that, yeah, sure, that's easy. We just do this item by item, use Excel. Fine, that means that for item 1, we need 2 in the store. That's the sparse recommendation, because with 1 we got 15 and with 2 we got 1%, so that's fine. With item 2, we need to go all the way up here, because we need to buy 4, because then we are below the 10%. So the stock recommendation for item 2 is 4. And then, of course, for item 3, the brown ones, you see, to get below the 10%, we need to go here. We need to buy 3 of that one, put in the stock. All right. Let's take a look at this in OPUS 10. So I'll close those ones. Open up this one. Start with the right one, hopefully. This one. Okay. So here we have that exact same scenario that I showed you in the presentation. So we have our 3 items. You see it here, 3 items. There we go, 3 items, 1, 2, and 3. I've calculated failure rates out of the mean time between failures. So yeah, 1 divided with the mean time between failures and so on. So we have them here. You see that the failure rate is way highest for item 2. I've also added as a stock allocation that minimum, or that the level that we calculated by hand according to the risk of shortage. So I said that it was 2 out of item 1, 4, item 2, and 3, item 3. So really I've been replicating that, and also we run an analysis now of this stock allocation. So you just run it, and you see we end up here. So, and now you see up in the left here, we're not looking at availability now. We can actually look at risk of shortage as well. So OPUS 10 can perform this calculation that I did in Excel and in that PowerPoint. We can do that directly with OPUS 10 here. So that means that we get here some kind of investment and a risk of shortage. And if we look at the table view instead, you'll see how, so these are the stock size, 2, 4, and 3, but we can add the risk of shortage as well. So I add the risk of shortage parameter here for the 3 items. You see this corresponds to the data that we had in the on this slide that we calculated. So for item 1, you see we have about 1% if we have 2 stock size, and for item 2, it's 6% over here if we have 4 in stock. So the stock size is 4 and 6%, and then it's 2.5% if we have, yeah, you get it. So just proving the calculation was correct, and with this stock size. Now, if we would open up this other file here and just run it without that's an initial analysis instead. Let's see. So what happens now is that I forgot to show you what the difference was on this file. What I did here, and what Opus also can do, is to add restrictions on the risk of shortage. So there is something called, just gonna make this a little bit more easy to follow, and then in the one called, there it is. So there's an input table called item station data. So I can give data for each combination of item station. And here I give this constraint of 10% maximum risk of shortage. Okay, so Opus, here, this is what I mean that Opus can calculate this as well. So we can get, we can say that we do not allow more than 10% risk of shortage for each of those item and station combinations. So what happened was that you see here for this curve, the orange one, it's on the first point, ended up on top of the other one, giving that same total risk of shortage and same cost. But then we also can invest more to produce more curves, points on the curve here to decrease risk of shortage. So that was just showing you how some people then use Opus 10. They say, okay, but I can calculate this with Opus 10. That's good. We set the maximum risk of shortage for all the item station combinations. Okay, but again, so now we are with this approach, we're controlling and limiting the optimization in a very tough way. So what we actually want to do is rather to let Opus 10 start using the system approach, starting from scratch, and optimize this instead. So what we've done here, exact same case. The only thing is that I've removed this item station data, this maximum risk of shortage limitation that we had before. So that means that without that, we open up for the standard system approach instead. And I ran it here, and it means that since we have no demands, we start from zero in stock, and zero in stock, as you know, as I showed you before, it's 100% risk of shortage. So that makes sense. And then we start to invest in stuff here, and when we come down here at the same cost as for the other solution, you see that we can actually get a lower system, total average system risk of shortage compared to what we had with the original one. Okay, how come? Well, now if we look again at the table view here, and we compare the risk of shortage between, I'm just going to select two cases here because that's probably easier. So what you see here is that for item 1, with the item approach, where we are limiting each of the items to 10% risk of shortage, we get this distribution of spares. But at Opus 10, when we let it optimize from the system approach instead, it says that, okay, no, just buy 1 of item 1, then you take 5 of item 2 instead, and then 3. So we change here, and we see that, so the risk of shortage is now 15% on item 1, but it's only 1.6 on item 2. And now the question is, how can this be better? How is it possible that it's better to have 15% than just 1% on this one? I think we move back to the presentation to try to explain this. So what happens here is we will look at item 1 and 2, try to analyze, try to understand why this is better. So with the item approach, The number of repair actions per year is 2 for item 1, and it's 17.5 for item 2. The number of repair action comes from the failure rate, so it doesn't change with the stock size. So that's constant. It's independent of the number we have in the stock. Okay, with item approach, we suggested 2 and 4. And with a risk of shortage of 1.2%, and